Hey guys, this is Mr. Brent, and this is 8.7 graphs of radical functions. So two things in this lesson are going to be graphs of graphing radical functions as well as identifying transformations of them. So one of our parent functions is the square root function. We're really just going to look at square root functions and cube root functions. But this is what the graph of a square root function will look like. They basically all look like this, except we can kind of flip them around, we can stretch them and move them around on the graph, but generally speaking, they look like half of a sideways parabola. Now, if we look at a table of values for this, and we just think about some of the nice values that are on here that have nice whole number square roots, we can get sort of a sense of why this looks the way it does. So if I plug in a 0, for instance, the square root of 0 is equal to 0. So that gives me this point right here at 0, 0. If we try 1, right, the square root of 1 is equal to 1. That gives me the point 1, 1, which is right about there. The next sort of nice point might be like 4. So if we do the square root of 4, that's equal to 2. So at 4, the height is 2. That'd be right about there. And the next one that'll fit on this graph is at 9, because the square root of 9 is equal to 3. So you can see, like, for every time that it jumps up by 1, every time that the y value jumps up by 1, the x value has to go up more and more. So this sort of, it continues growing, but it grows at a lower and lower rate as it continues off to the side. So then that last one, 9, 3, would be right about there. Notice that it does stop, though. It never stops going in this direction over to the right, but it does stop when it gets to the origin. If you think, what would happen if I plug in a negative number, right? So if I plugged in a -1, the square root of -1 is undefined, at least in terms of real numbers. On an XY graph, we can't fit it on there. So this, in your calculator, is going to give you an error. So it stops at 0. All right, a couple of things with this, domain and range. So remember that domain, these are the x values. So what are the numbers that I can plug into this equation? On the graph, it's how far to the left and how far to the right does the graph go. Looking at this, the furthest left I can go, x is equal to 0. So we would start at 0 with a bracket because 0 is included. And then, does it ever stop going to the right? Does x ever stop getting bigger? And the answer is no. And when that happens, when it never stops, that goes to infinity, and infinity automatically gets a parenthesis. All right, same thing with range, except now with the range, we're talking about the y values. And so again, this has a low point. The lowest point on the graph is 0 at the origin here. So that is 0 with a bracket. And then now it is a little deceiving. It looks like it's flattening out, but it does continue growing forever and ever. It just happens to be going to infinity on the x-axis faster than infinity on the y-axis. But the y is still going to infinity, so that one still goes to infinity with a parenthesis. Now, one thing about this one is once we start shifting this up, down, left, right, this origin point right here, that's this 0, 0, that is your domain and range, the beginning of your domain and range. If we shift this up and to the side, and so now it looks maybe like this, right? Now that domain and range has changed because the furthest left that we go is now at about 2, and the furthest down that we go is at about 4, let's say. So these numbers can change. The infinities will always stay the same, but this is always sort of like the beginning point of the radical, or of the graph. All right, next one is a cubed root function. Now, big difference with the cubed root function is you can take the cubed root of a negative number, right? Because a negative number cubed is still negative. So this ends up having kind of an S shape like this, where you can have negative values. Again, if we want to get sort of an intuitive sense of why this graph looks the way it does. Some of the nice numbers that would be on this one, -8. If we do the cubed root of -8, we get -2. And so that one at -8 has a height of 2. If we do -1, we get the cubed root of -1 is equal to -1, and so the height at 1 is right there. If we do the cubed root of 0, we get 0, so that is right there at the origin. And then the same thing with 1 and +1 and +8. We get +1 is the cubed root of 1, and and 2 is the cubed root of 8. So we also have the points 1, 1, and 8, 2. And of course, there's a lot of points in between, but those are the nice whole number points that we get on there. But notice we don't have a situation where we can get an undefined answer like we did with the last one. The nice thing about that, when it comes to domain and range, it doesn't matter if we shift these up, down, left, right, flip them around, stretch them, whatever transformation that we do to them, they're always going to be from -infinity to +infinity, no matter what. So both domain and range, -infinity to +infinity. All right, now let's talk transformations. In this format, we can follow this template. X will continue to be the variable, but then A, H, and K are going to be different constants that will affect how the graph is transformed from its parent function. The first one I want to talk about is H. This is your horizontal shift. If it is a minus H, it's going to move to the right, and if it's a plus H, it's going to move to the left. So it's a little bit kind of opposite of what you would think. One way that you can remember like which one is horizontal and which one is vertical, the H in this case, it's sort of inside the home of the function, right? This is kind of like the roof over its head. Sometimes we call those horizontal homies. So a horizontal homie moves left and right. Versus a vertical shift, this plus K on the outside, that's outside the home, so it's a visitor, it's a vertical visitor. Plus K is moving up, minus K is moving down. The next is a vertical stretch or compression. So this number in front, when you're multiplying by a number, that either stretches or compresses the graph. If this number is greater than 1, it's going to stretch, which makes sense. If you multiply something by a number bigger than 1, that result will be bigger. If the number is less than 1, not negative, the absolute value. So if it's a number like 0.5 or 0.8 or 1/3 or something like that, then it's going to compress vertically. And if A happens to be negative, that's what this is. It's not dash A, it's negative A. That means it's a vertical reflection, so it flips it over the x-axis. And sometimes we call that a reflection over the x-axis. All right, now when it comes to graphing, little asterisks by this. This can vary depending on your teacher. But this should be a good, if everybody did this, I don't think there's any teacher who's going beyond this. I think this would fit for just about everybody, but double check with your teacher if you have any questions about what their requirements are for your graphs. My requirements, I use the transformation to move the starting point or the center of the graph, meaning like where the square root function starts or the middle of the cubed root function. We want a minimum of 4 points graphed accurately. So you should be using your calculator, maybe even making a little table and plotting some accurate points. 1 point needs to be the start or the center, right? So if it's a square root, it's the starting point. If it's a cubed root, it's the center. And then if it is a cubed root graph, you need some points on both sides of the center. You can't have the middle point and then the other 3 points on one side. You need to have a little bit of a variety. All right, so let's take a look at what a couple of these look like. So square root function, I know the parent function, it kind of looks like this. It starts here and it goes like that. And so really what we're gonna do is we're gonna kind of grab onto this point here and we're gonna move it to wherever the transformation tells us to. And then we're gonna fill in a little table to figure out some points to use for this. Okay. All right, so looking at this, describing the transformation, we got a few things. This 2 right here, that is a vertical stretch. We're multiplying, so it's a stretch or a compression, and the number is greater than 1, so this is a vertical stretch of 2. And feel free to abbreviate as much as you see fit. All right, the next one here, that +1 on the inside, +1 moves it. It's a horizontal homie, it's inside the home, and plus moves to the left horizontally. So this will be left 1. And then the last one here, the -2 on the outside, vertical because it's a visitor, and minus is down, so down 2. All right, so the first thing I'm gonna do is I'm gonna, instead of being at the origin, it's gonna move left. So instead of being right here, it's gonna move left 1 and down 2. That's gonna be my new starting point. So if I plot that point right there. And now I like to make a little table of values for the rest of them. So x, y, if I plug in -1, I get -2. If I plug in 0, I get, and now what I mean by that is I'm doing 2 times the square root of 0 plus 1, and then -2 on the outside. If I plug in a 0, that result will be 0. So that's my next point. If I plug in a 1, so let me get rid of that. If I plug in a 1, I'm going to get 2 times the square root of 1 plus 1, with a -2 on the outside. And that's about 0.8. So that's about right there. And then if I plug in a 2, I get 2 times the square root of 2 plus 1 is 3. So 2 times the square root of 3, and then subtract 2 from that, I get about 1.5. So right about there. That's the minimum number of points. You could certainly plot more, but if we saw those 4 points plotted accurately and then sketched through, put an arrow on the end to make it nice and pretty, I think all of your math teachers would be very happy with that graph. All right, last thing is domain and range. So the domain, we want to think about how far to the left does this go. Horizontally, where does this exist? The leftmost point is the least horizontally, the least x value, that is -1. And then it just continues on and on until infinity as it goes to the right. So this is going to be from -1 with a bracket to infinity with a parenthesis. And then the range, same idea, but now bottom to top. So starting at -2, and then it never stops going up to infinity. And so that is -2 to infinity. All right, last one, same thing, but now with a cubed root function. So looking at this, we've got 2 transformations here. One of them is the horizontal homie, the -1. That is going to be a movement of right 1. And then we've got our vertical visitor of +2, so that is going to be a movement of up 2. So right away, the center of my graph, instead of being at the origin, it's going to be right 1 and up 2, so right about there. All right, now if I make a table of values, I'm actually going to do 5 total numbers here. I know the middle one, 1, if I plug that in, I get a 2, right? And I'm going to plot 2 on either side of this. So I'm going to go 0 and -1. That'll be on the left side of 1, and then 2 and 3 on the other ones. And again, you know, I'm doing like the cubed root of -1 minus 1 with a +2 on the outside. That's what it should look like in my calculator. All right, now on your calculator, if you're wondering about this, think, what class are you in? You're in math class. Hit the math button, and the third or fourth option down should be a cubed root option. All right, so that's going to be the cubed root of -2 with a +2. That's going to be about 0.7. And then cubed root -1 plus 2 is going to be 1. If I plug in a 2, it's the cubed root of 1 plus 2, which is 3. And then the last one, the cubed root of 3 minus 1 is 2. And that gives me about 3.3. All right, so if I plot in those 5 points, -1.7, 0, 1, 1, 2 I already had because that was my middle point, 2, 3, and then 3 and about 3.3. You can kind of start to see how this kind of makes that sort of swoopty looking thing like that. And again, that's not Mr. Grun's best work ever, but I think your teacher would probably be okay with that. All right, and then last thing, domain and range. Again, because this is a cubed root function, it is unbounded, which is kind of a nice, that's kind of a fun word. So both of them are going to be from -infinity to +infinity. It never stops going up, it never stops going down, left or right.